Yes, the recording is started.
Okay, great. So, in today's class, we will try to finish our previous chapter that we have started. So, the chapter was robot navigation. So, um, today's class will be a little bit shorter um, because we have just a few more topics to cover. So, I'm starting my screen. Let me know if you can see my screen or not. Can you see my screen?
Yes, you can see.
Yes, sir.
Okay, great. So in our previous class, we have talked about robot navigation and we discovered that navigation has three identical parts. First part is called path planning and second one is localization and third one is mapping. But to complete a mapping part, we need another part, which is basically the exploration part. So in our previous class, we have talked about uh, path planning and localization. Now uh, we are going to look into mapping and exploration algorithm. Okay. So, what does mapping mean? Mapping basically means that if you have an environment and you need to operate a robot within that environment, then you must need to know about the environment. Okay, so what do I mean by knowing environment? So if you want to know about the environment, you basically need to know where the obstacles are, where the vacant spaces are. So those are the information are very important to create a map. Okay, so in our mapping part, we will try to capture the location of the location of the objects within the environment, and based on the location of the environment, we will be creating a map. That map will help basically the robot to navigate itself around the environment confidently. Okay, so let's say and robot is moving in the environment. So if it doesn't know about the environment, then it will it may make some dangerous move, right? Which can damage itself. So, uh, to avoid these circumstances, we need to create a map so that knows in which way the robot can go and in which way the robot can't go. Okay, so that information is basically called the map. Okay, so this map will be generated by robot itself. We don't need to create the map for the robot. Robot can develop this map by its own. Okay, so now we will see that how a robot can create a map by extracting the information of the environment. Okay, so when the robot have the map in its hand, then it knows which action is valid for any specific location and which action is not valid. So as the robot is having the map, it can accurately navigate itself around the environment. We can expect that. Okay. Now, basically, there are lots of mapping algorithm, but in our course, we will specifically look into a single algorithm, which is called occupancy grid method. Okay, so occupancy grid method is a method which is used to create a map within an environment. It's a very what I can say, it's a very simple algorithm. The intuition is very simple, but it's very powerful. You can use this algorithm in any complicated environment you want. Okay, but the process is very simple. We will look into the process and the algorithm of this occupancy grid method. So let's say you have an environment like this. This is a real world environment, and you need to create a map of this environment. So how can we create a map of this environment? By using occupancy grid method. So as the name suggests, occupancy grid means you need to create several grids within an environment consist which will consist the information of the environment, whether the environment is having any obstacle in a specific location or not. Okay, so what is the process? Firstly, uh, you have to provide provide an information to the robot that what is the dimension of the room. Okay, this is the first information that you need to provide. So let's say the dimension of this room is 15 feet by 15 feet. Okay, let's say this is the dimension. Okay, so when the robot knows that the dimension is 15 feet by 15 feet, it will create a grid vault. Okay, it will divide the whole room into some identical grid. Okay, which we generally say cell. Okay, this is the grid or cell. Okay, so cell basically represent an individual component of the grid system. Okay, so that's basically the grid. And now the number of grid is can be varied. Okay, so if you want to, okay, just a minute. Okay, so what I was talking about, that you can create a specific number of grid in an environment. This is a variable. Okay, so let's say the grid size is smaller. You can make the grid size smaller, or you can make the grid size bigger. Okay, so if you make grid size smaller, that will make yeah, accurate mapping. That will create an accurate map. But if you are generating a grid world which is having a bigger size of grid, then it will create a little bit less accurate map. Okay, so when you are increasing the number of grid, it will also create a huge computational increase. Okay, so you have to trade off it between it. Okay, so whether you want to if you have a huge computation in your robot, then you can create smaller size grids. But if you have a limited amount of computational capacity in your robotic system, then you will create you will create a bigger size of grid. Okay, so the first thing which I've just told you, that you need to create a certain amount of grids which will divide whole environment into some identical squares. Okay, each individual grid can have three values. This is very important. Okay, so listen carefully. Each individual grid can have uh, three three of the values, either out of three values. Okay, so either a grid is can hold 0 or 1 or 2. Okay, so a grid cell will basically will have a value of 0 or 1 or 2. Okay, so each value represents a different type of state. Okay, So let's dig down into it. First of all, if a grid cell is carrying zero value, then this means that the grid cell is empty. Okay, the grid cell is empty. So what does empty means? Empty means this grid cell doesn't have any obstacle in it. Okay, so as you can see that this space is free space, right? This space is free. That means the grid cells which are situating here will be having zero values, because zero values are basically representing the free space. Okay, so as you can see that this white color is basically representing the zero value. So these are the zero values, and zero value represents the vacant space or the free grid cell. Okay, similarly, one if any grid is having one value, then this will represent obstacle. Okay, so if a grid is having a value as one, then this represents that this grid is having an obstacle in it. Okay, similarly, if the grid is having a value as two, this is basically means that you don't know about this grid. This in the grid is having an unknown information. Okay, so you still you don't know about the grid. It might have an obstacle in it, it might not, or it might not, but you don't know about this grid so far. Okay, so the information that you are lacking of those grids, of some grids, are basically representing with two value. Okay, so these blue colored cells are basically having two, that is basically represent the unknown state. Okay, so those grids which are holding two values, that those grids are basically having unknown information. You don't know about those grids. Okay, so that are the three states, that are the three types of values that a grid can have. Okay, now, so you can create any type of map you want. It can create any complicated type of map. This algorithm, as I already said, this algorithm is very powerful. As you can see that it's a very complicated map, but the occupancy grid method successfully have done it. Okay. Now let's look at the algorithm. How can a robot use this occupancy grid method to create a map? Okay, so it's a very simple process. Let's say you have a robot in this specific position. Okay, this in this location you have a robot, and this robot is having a sensor in it. Okay, this robot is having a sensor in it. So which sensor the robot can have? The robot can have a camera sensor, or the robot can have a ultrasonic sensor. So the robot will basically have a sensor which can detect the obstacle, which can detect the distance between the obstacle and the robot. Okay, so that is the sensor that the robot will need to have. Okay, so let's say the robot is having an ultrasonic sensor. So as the robot is having an ultrasonic or sonar sensor, that means it can detect the object, and it can measure the distance from the robot body to the obstacle. Okay, so let's say the you ran the code of ultrasonic sensor which can measure the distance, and the code returned a distance, and that distance is 10 centimeter. Okay, let's say the distance is 10 centimeter. So what does this 10 centimeter means? If an ultrasonic sensor returns a distance as 10 centimeter, what does 10 centimeter means? Can anyone tell me?
It's a depth.
Sorry?
I guess it's distance.
It's a depth.
Yes, it's a distance, but what does this distance mean?
Depth of the obstacle.
Yeah, exactly. So this 10 centimeter means that you have the robot has an obstacle 10 centimeter from its body. Okay, so the robot is having an obstacle which is 10 centimeter above. Okay, so this 10 centimeter is just representing this. So let's say let's say we represent this 10 centimeter as r. So as the robot is having a distance, and this distance is representing the distance between the obstacle and the robot. That means the robot is having a distance 10 centimeter above. Okay, so the grid cell, the grid cell which has a distance of 10 centimeter. Can you tell me about this grid cell? Which value the grid cell will have?
Sir, 0.
No, it should not have zero, because this grid cell is having an obstacle. We can clearly see that because it has returned a distance of 10 centimeter, and this 10 centimeter represents that this grid cell, which is 10 centimeter from the robot body, is having a obstacle. So as I already said that the grid cell which is having an obstacle in it will always have an one value. One is basically represents the obstacle, zero represents the, free space, and two represents unknown space. Okay, so this grid cell is 10 centimeters from the robot body. So, and our return distance is also 10 centimeter. That means this grid cell is having an obstacle in it. Is it clear?
Yes, sir.
Okay, great. So as this grid cell is having an obstacle in it, that means this grid cell should have a value of 1. Okay, should have a value as 1. So that is why you can see that a black color is drawn here, that this is representing 1 value. Okay, this grid cell is having 1 in it. Okay, so that's the first thing. So what we have found that if a grid cell is if a distance of a grid cell is equal if a distance of a grid cell is equal to the measured distance, which is basically the distance of the obstacle. If this is the case, then what should be the value of the grid cell?
1.
1. Then the grid cell should be 1. Now I have a question for you. The question is, the grid cell which is having the lesser distance than the measured distance, let's say this grid cell, or sorry, this grid cell or this grid cell, all of those grid cells are having lesser distance, right? Let's say if this is 10 centimeter from this robot body, then this should not be 10 centimeter. This should be less than 10, right? And this also should be less than 10. This also should be less than 10. So can you tell me what value should I put to these grid cells?
So in this case, R is a greater, right?
No. I'm asking you that the grid cells which are having less than 10 centimeter distance, what value should this grids will have?
Sir, 0.
Zero. Zero.
Yes, it should have zero, because
No obstacle.
as the, exactly as we have encountered an object 10 centimeter from the robot body, that means there is no obstacle in between that 2 centimeter 10 centimeter, right? That's why all of this grid cell is free. Okay, all of these grid cells are free. So that is why we have concluded that if the distance of a grid cell is less than r, if less than r means these grid cells, all of these grid cells are having a distance less than r. So in this case, the value of the grid cell should be 0. Okay, is it clear?
Yes, sir.
Okay, great. Now imagine a case where you have an obstacle in front of your robot, and the robot has successfully calculated the distance of this obstacle. Okay, so let's say you have a robot in this position, and you have an obstacle in this position. So when the robot is measuring the distance, it should measure this distance, right? By using ultrasonic sensor. But if another obstacle is like standing here, can this robot measure the distance of this robot or this object also, or not?
No, sir.
Yes, it can't measure the distance of the second object, because as we know that the robot measures the distance by using the sound wave. So it emitted a sound wave, and this sound wave is reflected from the first boundary that it encounters. So this is the first boundary. So the sound will get reflected from this surface, and it will come back to the robot. So as although the robot is environment is having another object just beside the object, but this can't be reachable for the robot. And this object will be reachable if the robot will like move to another place. Let's say the robot is move to this place, and that on that place the robot can measure the distance. Okay, but when the robot is here, it can't detect this object. Okay, so that means that we have measured a distance which is r, or which is 10, so that the grid cells which are apart from this 10 centimeter, or the grid cells which are having a greater amount of distance than 10 centimeter, those grid cells will have a value of, can you tell me which value those value will be, those grid cell will have?
2.
1, 2, or 0?
2,
2.
sir.
Yes, it will have 2, because we don't know about those grid cell so far. Okay, that is why this grid cell will have 2. This is will 2, this will 2, this will 2, this will 2. Okay, so the last point is, if the distance is greater than r, then the value should be 2. So conditions that an occupancy grid method uses to create the map. And when a robot is completes one step, it just can detect a specific object, and to know about another object, it needs to go to another place. Okay, it needs to go to another location, it needs to move its position to another position, so that it can cover another distance, it can cover another region. Okay, so let's say the robot was situating here, or was standing here. So after detecting this object, it has created some values, right? It has updated some values. But after completing this step, it will go to another position. Let's say it has gone to this position. Then after going to that position, it will start to detect another object again. And after detecting that object, it will try to like measure the distance again, and then by using these three condition, it will update the map again. Okay, so as you can see that the robot will create a map of this environment by putting 0, 1, or 2 uh, in the in the grid cell. But to do so, to complete a full map, it needs to move from one place to another, so that it can cover the whole environment. Okay, so is it clear to all?
Yes, sir.
Is it clear?
Yes, sir.
Okay, great. So the conditions that we have talked about the conditions are written here. So the first condition, the second condition, third condition, the third, these are the three conditions, and we call those conditions as region 1, region 2, and region 3. Okay, and this conditioning is called better sensor model. Okay, so if you are using these conditions to create your map, then you are using a better sensor model. Now you can ask me, sir, you have already talked that this is basically the occupancy grid method, right? Yes, it is occupancy grid method, but the conditions that we have looked into is basically created for a model, and that model is called better model, a sensor model, a better sensor model. Okay, there is an another model which is called the simplest sensor model, but that is not going to be used in our in any of our yeah, in any of our algorithm. That's why we are omitting simple sensor model. Okay, rather we are using a better sensor model. So a better sensor model is the pillar of the occupancy grid method. Okay, so we will create our occupancy grid method. We will use our occupancy grid method by using a better sensor model. Okay, so now, okay, so now let's wrap the whole algorithm up. Okay, firstly, what we need to do, firstly we need to initialize the grid, right? I already talked to you, I already said that when you give the dimension of the room, the robot will first create, the robot will first divide the whole room some some unique sized grid cells, right? And all of those grid cells will be initialized as unknown value. Okay, at first when the robot is not being when the robot has not started doing the math, so it is the preliminary stage. The robot just created the grid cells, just divided the whole room into some specific size grid cells. So it must need to give some values to the grid cell, right? Because this is basically a 2D array for a robot. Okay, if you compare this with your data structure courses, then these grid cells are nothing but it's basically the 2D array or a matrix or a 2D matrix. Okay, so as you are having a 2D array, you must need to give some value to any at each individual elements, right? So what should be the value when the robot doesn't haven't started doing the math? So at the at the preliminary stage, all of those grid cells value will be 2 because we don't know about the map yet. But when the robot starts to do the map, then the robot will gradually update the map by using one or two value, one or zero values. But before doing the mapping, it will initialize the whole map as unknown value, as unknown state, or as as value as 2. Is it clear? Is it clear?
Yes.
Okay, great. So after initializing the map, that position will be marked as an empty position because it must be empty, right? We can't put a robot in an obstacled position, right? We must need to input the robot in an empty position. So the robot will first mark its position, the position there where the robot is standing, as empty. Is it clear, or do you have any question regarding this?
Yes, sir, clear.
Okay, great. So the first thing is, when we are updating the grid, I'm talking about the updating part. When we are updating the grid value, firstly, when the position where the robot is standing will be identified as an empty space. Then the robot will use the better sensor model. So what is the better sensor model? The better sensor model is basically the conditioning part. We have talked about three conditions, right? At first r is greater than distance is greater than r, distance is equal to r, distance is less than r, right? So we already know which better sensor is. So we will use that better sensor model technique to update the map. So after completing the step one, it will create some value. It will update some values, right? It will make some grid values as 0. Some grid values will be updated as 1. Okay, so that is the first step. So after updating a first step or after completing first step, what the robot need to do? Can you tell me what the robot needs to do after completing the step one?
It goes
Can
to
you tell
step
me?
two.
Sorry?
It goes to step two, right?
Yeah, it needs to go to step two, but what is the step two?
To mark it either empty or occupied.
Yes, we have already marked as some places as empty or obstacle by using the better sensor model. I have completed the step two. My step two, or sorry, I have completed the updating the grid part because it just completed the step one. Because what the step one means? Step one means this part. Robot was standing here. It calculated that this grid should have one, this grid, this one, all of those grid will have 0. So this part is done. Now what can we do? Our map is not done, right? We need to know about, we have lots of areas to cover. So what can we do now? It's a simple question. What can we do now? We just completed a specific part of the environment. Now what can we do?
Now we have to do for the rest part.
Exactly. So we need to go for the rest of the part. So how can we go to the next part? We need to uh, we need to move our robot to a new position. Okay. So the position where the robot was standing, it has done its work. But to cover another region, we need to move this robot to another position, right? So that the robot can cover another distance, or can so that the robot can update some other values of the grid cells. Okay. So the third step is the third point is we need to pick a grid. So this is very important. We need to pick a grid where we want the robot to go. Okay. We need to efficiently pick a grid where the robot needs to go. Okay. To perform its step two. Okay. So firstly, we can say that we can randomly go to a position. Let's say if we pick the next new position randomly, is it useful or not? Let's say. So let's say that robot was standing here, and it has completed mapping this region. Okay, in step one. Okay, now what we are saying that we are picking our next move randomly. If we are picking our next move randomly, that means the robot can move to this position, right? Maybe this position is randomly taken. Okay. Now, as the robot has come to this position, that means the robot will now start to do its mapping again. Okay. This is basically the step two. But as you can see that when the robot will start to do the map from this position, it may cover this region. Okay. But as you can see that the region that our previous position, this is the position one, let's say this is the position two. So in our position one, we have already covered a region that is getting overlapped with region two. So when the robot is performing step 2, it is double calculating some part for some of the parts, right? So we are getting redundant data. We will just get some extra information of this part, but most of the part that the robot will cover is already being covered in our previous step, right? So as we are taking a random move, that will create a huge problem to us. That will create a huge delay in completing the whole map. So can we say that can we say that randomly if it is not efficient to take a random move in mapping? Can we tell that? Is it clear to all? I mean, if we take any
Yes, sir.
random move, that will not create an efficient way of doing mapping. Okay, so we need to come out with some optimal way to choose our next move, so that the robot needs a less amount of time to complete the whole map. Okay, so the mapping, normally in a room, a mapping is a very tedious process. It needs a lot of times to complete the whole map. But if we can't take our moves optimally, then it will take more than like uh, 2 times or 3 times greater than the time that the optimal moves can take. Okay, so that's why now we are going to look into how can we choose a better cell where the robot can go to perform its next step, so that the mapping will be effective or time efficient. Okay, so is it clear to all that what we are going to do now? Is it clear?
Yes, sir.
Okay, great, great. Now, now we are at step 3, right? We are at step 3. Now, I will I'm pausing you here. I'm going to talk about how can we pick a next move by using an optimal algorithm. We will get back into it again, but now we are going to a next topic that will help us to pick a next move efficiently. Okay, so we will now go to another topic, that is basically the technique which is responsible for for picking a next move efficiently. Okay, so what that is called. Okay, so that topic is called exploration. Okay, so that is why I have told you that exploration is not an independent topic. It's basically related to mapping. Okay, because we are in mapping process, but before completing the mapping process, we are taking a pause, and we are inheriting we are adding the exploration process into it. That means exploration is not an independent process, it's within the mapping process. Okay, good. So now let's look into the exploration process. So now, what does exploration can do? Exploration is nothing. It's basically nothing but it basically the way how you can choose a better node, or how can you choose a better grid where the robot can go and can make its map efficient. Okay, so the technique which we will look into is called the frontier based exploration. Okay, so the frontier based exploration will be used to create or to choose a better cell for the robot, so that the robot will need a less amount of time to complete the whole map. Okay, now what is the frontier based exploration? So before knowing about the frontier based exploration, we need to know a special term which is called frontier cell. okay, or frontier grid, okay. So what a frontier cell or frontier grid means? A frontier grid means within an environment, let's say this is an environment, and this environment is having grid cell, right? It has a lots of grid. Okay. So the grid cell either can be one or can be zero or can be two, right? We have already talked about it. That each grid cell either will be one or two or zero. So two means it is unknown, one means it is obstacle, it has an obstacle, zero means it is free. Okay. Now within this whole set of grid cells, some grid cells will be identified as a frontier grid cell. Okay. Now which cells will be considered as frontier grid cell? We need to know about it. Okay. So if a grid cell wants to be a frontier cell, then it must be an unknown cell. It must have to be an unknown cell. Okay. So it has to be an unknown cell. That is the first point that the grid cell needs to match. And the second point is the grid cell, which is also which is all obviously an unknown cell. This unknown cell must need to have at least an empty cell around it. At least an empty cell around it. So what does around means? Around means, let's say we are considering if this is a frontier cell or not. So when we are considering, when we are checking, we first need to check if it is having a two value or not. Okay, if this is having a value of 2, that means this is unknown cell. That means the first condition is done. And the second condition is we need to check if it is having any sorry. So if we need to check that if it is having any free cells around it or not. So what does around mean? Around means the upper cell, the right cell, the left cell, or the bottom cell, or the down cell. So those four cells will be considered as the neighbor cell. Okay. So we need to check that within these four neighbor cells, if there are any cells that is empty or not. If we find that yes, this is empty cell, that means this should be considered as frontier cell. Okay, so let's try to identify the frontier cell. Okay, so let's say uh, this is the whole grid cell, and here gray color means unknown cell. Okay, gray color means unknown, white means free, and red means occupied or obstacle. Okay, so can you tell me, is it possible that this grid cell is a frontier cell? Is it a frontier cell?
No, sir.
No, sir.
Why not?
Frontier is just next to the white node.
Yes, it is an unknown cell. The first condition is met, but it doesn't have any empty cell around it, right? That is why it should not be an frontier cell. Now, is it a frontier cell?
No, sir.
No, it can't be a frontier cell because it is failing at the at very first point, right? So it is not an unknown cell. That means this can be a frontier cell. Now, is this a frontier cell?
Yes, sir.
Yes, it is a frontier cell because it is an unknown cell. The first condition is done, and it is having two adjacent free space, right? This is a free or empty cell, and this is also an empty cell, which is enough to make it as a frontier cell. Okay, so this is a frontier cell. So is this a frontier cell? Is this a frontier cell?
Yes, sir.
I Okay, great. So bear with me. Is it a frontier cell?
Yes, sir.
Okay. Is it a frontier cell? Is it a
Yes, sir.
frontier cell?
Yes, sir.
No, no. It's not a frontier cell because this this cells is unknown. It is having an free space, but this is not the adjacent, or this is not the neighbor cell, because neighbor cell will be, I already talked about it, that neighbor cell should be. Okay, so when we considering this, neighbor cell will be the upper cell, the down cell, the right side cell, and the left side cell. Those cells will be checked, but the diagonal cell will not be considered. So this cell, I'm talking about this specific cell. This cell is having a empty cell, but it is a diagonal cell. So we will not consider it a diagonal cell. Okay, is it clear?
Yes, sir.
Okay. So this is also a frontier cell. This is also a frontier cell. This can be a frontier cell. This can be a frontier cell. And then this should be a frontier cell. 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 This can be a frontier cell, but this should be a frontier cell. So those are the frontier cell that we have identified. Okay. So we have identified the frontier cells. Now, as we have identified the frontier cells, now what can we do? So what though that frontier cell is doing? The frontier cell tells you that when the robot is doing the mapping, at any specific step, after calculating the frontier cells, the robot can take any frontier cell it wants. All of those frontier cells will uh, make the mapping algorithm efficient. Okay, so that is the frontier based exploration technique tells you. Okay, so frontier cells exploration says that you can choose any frontier cell you want. All of those frontier cells will eventually create an optimal mapping for your robot. Okay, so in our previous discussion we are talking about that we can't take any random move, right? But this frontier based exploration is saying that you do not take any random move, rather you take a frontier cell as your next move. This will create an efficient way to do the mapping. Is it clear? Is it clear to all?
Yes, sir.
Okay, great. So that means we have a lots of candidates. I'm saying that candidates means the frontier cells. We can choose this one or this one or this one or this one or this one. When the robot is here, it needs to take another next move. Then when it needs to take a next move, it can take this. It can go to this place or this place or that place. Okay, so that it can do the efficient mapping. Okay, now to choose from the frontier cell, we can still do some extra optimization so that the frontier cell choosing becomes more efficient. Okay, so how can we choose frontier cell efficiently? So to choose frontier cell efficiently, we can choose the closest frontier cell first. Okay, so that can be a case because the closest cell is this one. So if you choose this, you can directly go to this place and start doing map again. But if you choose this cell, because yes, it is a frontier cell. You can choose this cell, but if you choose this cell, then you need to go a lots of distance to arrive to this position, right? So this will take a lots of time. But if you choose this cell, before going to that position, you can even make another step of mapping, right? That's why closest frontier cell will get preferred when you are choosing the frontier cell. Is it clear?
Yes.
Okay, great. So that's all for the exploration part. Now let's come back to our mapping algorithm. So what we are talking about, picking a next move. Now we have talked about the exploration technique. So now we will use the exploration technique to pick our next move efficiently. So as we are using our exploration technique, we can effectively take a next move. Then after taking that next move, we need to go to that position. Okay. So we need to go to that position, which position we have taken as the optimal take, which is basically the frontier cell. Okay. So we need to go to that frontier cell position. Then we will loop forever. We will go to another again that step two and then do again, then do again, then do again. Okay. So that is the occupancy grid algorithm. So this algorithm will help you to create an efficient map of the environment. Okay. So the robot will use this method. The robot will use this algorithm to create the whole map. Okay. So that's all for navigation. So we have completed all of those parts of the navigation. We have talked about the path planning algorithm. We have talked about the localization technique. Then we have talked about the mapping and lastly the exploration. Okay. So now, do you have any question regarding any of the part? Do you have any question?
No, sir.
Okay, great. So our navigation chapter is done. So I will take a quiz on this navigation chapter. So maybe it will. I will take your exam on next Thursday. Okay, next Thursday. So be prepared. Your first quiz will be on next. Sorry, your second quiz will be on next Thursday, and I will take your last quiz. Um Okay, I will try to complete this control theory class in this running week. The week is just started, right? So I will try to take two classes on control theory in this week so that you can give your quiz 3 with your own section. Okay, I will try to do that because if you can give your quiz with section 6, that will make less difficult for me. Okay, because it's difficult for me to make another slots to take quiz for you, but uh, I have already taken quiz 2 for all of my sections, so you need to give your quiz to just like how you gave your quiz 1, but I will try to match with the content that I am uh, I'm teaching in my regular classes so that you can give your quiz 3 within the class with the section 6. Okay, is it clear?
Yes, sir.
Okay, great. So that's all for today. So we'll be meeting at my desk on next Thursday. I will give you a time where you will need to come to give your quiz. Please remind me before like Tuesday or Wednesday, so that I can make a free slots for you. Okay.
Sir, I guess
So
after 5 will be better on Thursday.
after 5. Okay.
At,
So
at 5, I mean.
okay, after 5 will be difficult for me because I have classes at, I have classes my class ends at 3:30, so I need to uh, like spend a lots of time in the campus without doing anything. So I will try to give you another time, but that quiz will not have a lots of time. It will just take 20 or 25 minutes. So you can give your quiz and go to another regular class if you have. Okay. So you can, it's a request from me that please make a slot for me from 3:30 to 5 p.m. if you can, so that you can give your quiz and go to your class, regular class.
So I
Tell
have
your
class
faculty.
that time from 3:30 to 5.
So sorry.
I have class at that time, 3:30 to 5.
Okay, so you have a class from 3:30. Okay, so do you have any class from 2 to 3:30?
No, sir. No for me.
Okay, so I will talk about this uh, in the Discord channel. Don't worry, so that we can fix a time that suits for all. Okay, but if we don't have any other option, then yeah, I will take your quiz at 5 p.m. But I will try to match with another time slots. Okay. Okay.
Okay.
So so that's all for today. Thank you for joining. I'm ending the class. Thank you.
Oh, thank you, sir.
Thank you.